Okay, good evening, everyone. Welcome back. Advent of Code. Advent of Code 2024. I keep forgetting which year we're in. Um, we're going to do day 6 today. Obviously, I'm a couple of days behind. That's just how it's going to be. My name is Savani. This is the channel where you get to watch how a 25-year computer programming professional can sometimes struggle with just as many problems as everybody else can. It's also, it occurred to me tonight, this is the place where I can practice explaining my thoughts as I'm writing code, which, whether it makes me a better programmer or not, might make me a better coworker. So that's actually kind of a bonus that I'd never really thought about before. I always thought of this as like the golf practice, the place where I kind of work on figuring out how to just solve problems more quickly, think on my feet, that sort of thing. But we'll just take that extra potential win. I'm going to come over here, bring over the Advent of Code. Turn my volume down a little bit more. It's still just a little loud. There we go. That should be low enough, finally. And get rid of that. Here we go. I still haven't figured out what the picture that is slowly appearing is, but, you know, eventually. So, problem number 6. Now, I've already looked at this one, and I know that at least part A is going to be very easy. This could be a short night if part B also turns out to be pretty easy. But we're just going to jump right into it. The historians use their fancy device again, this time to whisk you all the way to the North Pole Prototype Suit Manufacturing Lab in the year 1518. Interesting. At some point, I'll look at what that's about, but this leads to 2018. It turns out that having direct access to history is very convenient for a group of historians. You still have to be careful of time paradoxes, and so it will be important to avoid anyone from 1518 while the historians search for the chief. Unfortunately, a single guard is patrolling this part of the lab. Maybe you can work out where the guard will go ahead of time so that the historians, all caps, note, so that the historians can search safely. You start by making a map of the situation. For example, all of this. So, the map shows the current position and facing of the guard. This up arrow indicates that the guard is facing upwards. And any obstructions. So the obstructions are these hash signs. Zoom in even further here. So they are very strict in their protocols, which involves repeatedly following a very simple set of steps. If there's something directly in front of you, turn right 90 degrees. Otherwise, take a step forward. So this guy is going to continue walking forward, going up until he hits this obstacle right there. And then he's going to turn right and go this direction. And then he's going to turn right again and head down to this obstacle. And this is just going to continue on. So, following the above protocol, the guard moves up several times. Yep, here we go. Until she reaches an obstacle. And we keep on going. There's a downward V. I don't know what that character is. We'll have to find out. Anyway, so by predicting the guard's control route, I can determine which specific positions in the lab will be in the patrol path, including the guard's starting position, the positions visited by the guard before leaving the area, which seems like an odd behavior for a guard, but that's okay. The positions visited by the guard before leaving the area are marked with an X. Okay, that's pretty cool. So the guard will visit 41 distinct locations on the map. So I want to predict the path of the guard, and then how many distinct positions will the guard visit before leaving the mapped area. And the map The map is pretty large. This is 130 spaces wide by, okay, it's definitely a square. 130 by 130. So this is a really big location. But of course, if it wasn't a big location, I would just like brute force the solution. We're not going to do that. Now this one's going to be really easy because I wrote a grid for one of the problems several days ago, and I've already taken the liberty of extracting that grid into its own crate, making some very small tweaks to enhance it a little bit. But really, we're just going to reuse exactly that. We barely even have to do any parsing on it. Because already the grid is, in fact, we don't have to write any parsing code tonight. The grid is already set up to figure out the height and the width of things, to break it into lines, to then break each line into characters, and then to store all of those characters. I can just work on the character data. We also already have the code to move things around the grid. Might need to make a modification. Maybe not, actually. Returning none when something will run off the edge of the grid could be beneficial. So yeah, that's where we stand right now. So I'm going to jump into day 6 here. We've already got our basic test input. So I'm going to start out with, as always, the most obvious test, which is it finds the guard's distinct locations. So we're going to let grid equals grid from test input, and then assert that distinct locations of the grid and the guard is 41. There's a lot of unanswered questions here, though. First of all, why isn't it detecting test input? I think my editor just hasn't caught up. The guard, I'll just create a new guard. This is probably wrong. Well, it's definitely wrong. I know it's wrong, but that's beside the point. Okay, there we go. We've got some scaffolding in place now. We'll save it. The compiler is not happy because I haven't imported grid yet, so use crate grid. There we go. And now get the test suite running. Cargo watch -x next test run. Oh, I broke day 4. I thought I made sure that would still work. And now day 5. No, I didn't. All of these. Okay, the output confused me. This new test is failing. There's a whole bunch of disruption in the middle, but then day 4 and 5 are both passing. Good. I had thought that I extracted the grid without breaking day 4. So once that particular test passes, then we know that we're ready to try it against the real data set. So now I want to find the guard. So test fn it finds the guard. So the guard is located right here. So this location is 0, 1, 2, 3, 4, 5, 6. So it's 6 down by 0, 1, 2, 3, 4. So 4 across. So assert EQ guard location is 4 by 6. So guard location, I need to find the grid, or I give it the grid in order to find the guard location. And there's a degree to which I think that instead of just finding the location, I want to say find guard and expect to get back a guard. And while we're at it, we don't have to get just the location, we can also get the orientation. So I come back up here, say location is an I-32, I-32, and then orientation is a direction and so far so good. Probably I am going to delete this constructor for the guard and come back here. I don't think I even need to be passing the guard in here. This function can find the distinct locations for the guard. And by the way, at the moment, I can't even begin to predict how I'm going to have to change the problem to solve part B. We'll get there when we get there. And this orientation is incorrect. The orientation should be north. So I'm going to do this in basically the most dirt simple way possible. I'm going to scan each location, and when I find one of these arrows to represent the guard, that's going to be where the guard is. So for x in 0 dot dot grid dot width, for y in 0 dot dot grid dot height, match grid dot lm xy against, what does lm return? Returns a car. Okay. So if it's a dot, we do nothing. If it's, in fact, that's being overly pedantic. It's really just going to be, if it's an up arrow, we're going to do something. If it's a right arrow, we're going to do something. If it's a left arrow, we're going to do something. And if it's whatever this particular character is, that might be a lowercase v. Yes, that's exactly what it is. Okay, I feel a little silly there. Let direction, or let orientation equals this. And if it's anything else, the orientation is none. So direction north. east, west, and south. Okay, so now if it's one of these four, it's going to be an orientation. So if let sum orientation equals orientation, i.e. if we have just found the guard, we know which direction the guard is facing and we know the address. So we will return her. So guard location is going to be XY, and orientation. And I'm just going to panic right here. I'll quickly get the syntax working again. Ooh. Yes, right. Oh, I botched a couple of different things. Delete. There we go. That should be better. That all works. Expected this to be, yes. We're going to return the value. X and Y, they are U sizes. Yeah, we'll just say as I32 and I32 and be done with it. Okay. And guard does not implement. I know a couple of things that it doesn't implement here. So we're going to implement debug. We'll implement clone, debug, and partial EQ. And then we'll check the tests. Direction can't be compared. That's fun. Copy, clone, debug, and partial EQ. Cool. So, finds the guard's distinct locations, is failing, but it finds the guard just fine. Not a problem at all. So, next, if I know where the guard is, now I just want to start moving the guard. So this is running a simulation. Whoops. So I think what I want to do is create a function here, which is fn simulate path grid and the guard, and I kind of want to just return I care about the distinct locations. I'll just return a vector and then later on collapse it down. So it's going to be a vector of I32, I32. And we'll make it an empty vector. But now that we have this simulate function, we can fill out the distinct locations function. So let path equals, well, first let the grid no, I got the grid. Let the guard equals find guard for the grid. Then let path equals simulate the path for the grid and the guard. And then I want to convert path into a hash set. And again, there's no like from operator. This is turn the vec into an iterator and then recollect it. So it's going to be path.intoIter.collect as a hash set of I32. And then I don't even want to, well, I did collect it, but I don't want to do anything with it except figure out the length. I can convert a U size to an I-32 and oh, fine. Here I'll actually use a U size. Consider removing this method call. This receiver has type... What? Well... Oh. Yeah. The compiler is right. The compiler is always right. Okay. Still returning 0, which is expected because I'm returning an empty vector from the simulation function. So now it's time to write the simulator. And the simulator is, I think in this case, it's going to be pretty easy. We know where the guard is. We've got the grid. We're going to call this move function that I have on the grid repeatedly, and we're going to check the result. So let's see here. We're going to move the pointer. In fact, it's going to be move the pointer and retrieve the element at the pointer. If the element is empty, update the guard's position. If the element is an obstacle, turn the guard. If there is no element, return the entire path. That's actually really easy. So the way we translate this, first of all, let location equals guard.location. We'll make this mutable. Now, now I'm having a problem of priming the problem. So it's going to be a little bit awkward for the moment. We're going to say grid dot let next equals grid dot move pointer location dot 0 location dot 1. Now, while grid dot lm well, it's actually while let sum of next equals next. So, like, in fact, now we can collapse just a little bit, make it a little bit more elegant. Move pointer location dot 0 location dot 1. Okay. So if we've done a move pointer and we get some value, then we haven't gone off the grid yet. Cool. Why is it angry with me? That's why it's angry. I haven't told it the direction to go. There we go. So now we get the match grid.lm at next.0 and next.1. Yep, with a dot. For the moment, just make everything unimplemented. I'm going to catch all of the match arms first. So a dot, a hash, and it actually shouldn't be anything else. Those should be the only things that I find. Well, except for the location of the guard, or the initial location. Which I think there's a cleaner way to do this, but I'm basically just going to make all of these treated as though they are empty. Is this the syntax? I think this is the syntax. Yeah, because it's not complaining about syntax errors, it's complaining about mismatched types, so it's getting beyond syntax analysis. Okay, for all of that, it's unimplemented. Everything is failing. It's very angry with me. Return vec. Actually, let mute path equals vec. Here we return vec no matter what it is. Path here is a vec of I32. That should make quite a few things happier. Now move pointer. What? Why did I make these U sizes? If y is greater than equal to 0. Huh. I actually managed to write this function so that it is safe to use a variable that can never be negative without having to do any kind of weird typecasts. Go me. That's kind of amazing. I'll appease the entire thing. I have no idea what keystrokes I hit. That is not the file I was just editing. Oh, and now it's indexing my whole root files, home file system. Wow, okay. It's amazing the things that Vim can do, and I have no idea what all of them are, and I've been using Vim for 30 years. Okay. That should be close. I'm going to remove those. Vec is not a... Yeah, actually, you're right. Vec is 100% not a value. Path, however, is. Okay. Cool. So that gets all of the branches handled. We should get some unimplemented. Yeah, there we are. So not implemented. Cool. That's exactly what I expect right now. Okay. So if the next location is an obstacle, we are going to change the orientation of the guard, but we're not going to change the position. So guard.orientation equals next orientation. Well, let's call it right 90, actually. In fact, let's be even nicer. Guard.orientation.right 90. Just create a new method on this direction structure. IMPL direction fn right 90 self returns well, another self, and we'll leave that unimplemented. Okay, and then the next one, if it's one of these, the space is clear. We already know what the new location is. We're just going to assign that to the guard. This is the new location right here. So we'll say guard.location equals next. And okay, that's good because I think I was about to infinite loop it because I never update this location variable. I don't really know. I feel like I'm having to use one more variable than I want to. But we're going to do it. Location also equals next. Continue on. Okay, it's still angry about the guard mutability. And that's fine. I'll clone the guard. That way I can have a mutable copy. We'll do that. Need to make sure to push the next location. Also need to start out with a location already containing, or with the path already containing the guard's location. So we'll do that. And now I don't need to specify the vector type. So now path.push, yeah, location. Okay, cannot find the guard. Why not? Oh, because parameter passing syntax gets really weird. Okay. Problem on line 23. Oh, it's not happy with me still. What's not implemented? Oh, I never implemented right 90. So match self against direction east becomes direction south. West, direction west becomes direction north, and direction north becomes direction east. But there's also these other four, and even though we're not using them for this problem, I'm going to go ahead and fill them out. So southeast, southwest, northwest, northeast. So if we're going southeast, 90 degrees is going to be southwest. If we're southwest, we're 90 degrees to the right will be northwest. Direction northeast, and then again direction southeast. And this linter warning is wrong, and the test passes. So we're ready to run against the real data set. So let the grid equal grid from input, and then format the result of distinct locations on the grid. And now I'm going to run it for reals. Cargo run 6A. Okay, 4,602 locations, which is not all that many if you consider how big 130 by 130 is. Got it right. Cool, cool. I said this was easy. We're already 40 minutes into the stream. Yes. Engineers and our ability to estimate time. Part 2. While the historians begin working... Oh. Before I do that, all of the normal thing, assert EQ, distinct locations, grid, 4602. And okay. Now we're going to come back again. So, while the historians are working around the guard's patrol route, I borrow their fancy device and step outside the lab. From the safety of a supply closet, I time travel through the last few months and record the nightly status of the lab's guard post on the walls of the closet. Okay. So, returning after what seems like only a few seconds to the historians, they explain that the guard's patrol area is simply too large for them to safely search the lab without getting caught. Fortunately, they are pretty sure that adding a single new obstruction won't cause a time paradox. They'd like to place a new obstruction in the way such that the guard will get stuck in a loop, making the rest of the lab safe to search. Yeah, I thought this was going to be tricky somewhere. So, to have the lowest chance of creating a time paradox, the historians would like to know all of the possible positions for such an obstruction. The new obstruction can't be placed at the guard's starting position. The guard is there right now and would notice. But wouldn't notice a new obstruction placed there in their line of sight, of course. In the above example, there are only 6 positions where a new obstruction would cause the guard to get stuck in a loop. The diagrams of those 6 situations use O to mark the new obstruction, a vertical bar to show the position where the guard moves up down, a horizontal bar to show a position where the guard moves left right, and a plus to show a position where the guard moves both up and down and left and right. Okay. I kind of get it. I think there's a lot of extra stuff here that doesn't factor into the solution, but only factors into the description. So if we place an object right here next to the guard's starting position, the guard will hit the first obstacle, turn, hit the second obstacle, turn, third obstacle, turn, the new obstacle, turn, and be back on the path to the first obstacle. There's another option here. Bup, 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 bup. So this one doesn't ever get the guard back onto the original path. The guard goes north, east, south to here, west to here, north to here, east, hits this one, comes back to here, runs this path again, and just ends up in a loop right here. Okay. So there's a whole bunch of these. Doesn't really matter what I choose to use as an obstacle so long as I and the historians can put it into position without the guard noticing. The important thing is having enough options that I can find one that minimizes time paradoxes. And in this example, there are 6 different positions that I could choose. So I need to get the guard stuck in a loop by adding a single new obstruction. How many different positions could I choose? Yeah, this one... I mean, I think I could brute force this. Just test each location and see if the guard ever gets stuck in a loop, which would basically be defined as the guard ends up at a location and with an orientation that the guard has been at before. That's pretty easy to detect. Oh, I don't have to test the entire map. I only have to test the path that the guard would ever be on. Because if this obstruction wasn't here, then the guard would continue walking until she hit this obstruction. So I don't have to test outside of the path that I've already determined. I'm glad that my simulate function returns the entire path. So let's see here. Let loop OBS equals looping obstructions on the grid. Now we're going to assert that within OBS, which by the way is going to be a hash set of locations, contains 0, 1, 2, 3 by, well, this is going to be 6 because it's right next to the guard. So it contains 0 by 6. And the next one is at 0, 1, 2, 3, 4, 5, 6. 6 by 7, we're one further down. And another one at 7 by 7. This is just one over from this one. And then 1 by 0, 1, 2, 3, 4, 5, 6, 7, 8. And then 2 over from that, so 3 by 8. And then finally 1, 2, 3, 4, 5, 6, 7, 8 by 9. So those are the possible solutions for the test case. I have to take references to each of these? Okay, sure, I'll do that. Okay, So the first thing I want to do is I want to grab the original path. And for that, I even want to enhance the path just a little bit. Which, in a sense, this is going to look a little weird, but it actually means that I want every state of the guard in a vector. We'll see in a moment. I'm probably going to have to derive some more things before, like I'm probably about to break the first code, and we'll have to derive some more things. But instead of just pushing the location, we're going to push an entire clone of the guard. Yeah, did not. There we go. Okay, all of that's okay. Value hash set cannot be built. Oh, 25. Yep. Guard. Okay, and guard does not satisfy a particular trait, so we're going to do that. And that's going to require that direction also satisfy the trait. So we'll derive that. What else do we need? And we need a strong equality. Okay, everything compiles, everything runs. The guard's distinct locations are now failing. I'm getting 45 of... Oh, no. Okay, yeah. This one doesn't care about the guard's orientation, and I broke the original one because now, like, the guard might hit a location more than once, but in different directions. By just taking a bunch of snapshots of the guard, I end up having some uniquenesses there that I don't want. So path.into_iter, we're going to map this guard.location. So we only care about the location, and then we're going to collect it back to, and this should give us back the level of uniqueness that we care about with distinct locations. Okay, perfect. We're back down to only the looping obstructions failing. Okay. So for the looping obstructions, I want to figure out the path that the guard took. Yeah, okay. Let guard equals find guard. Then let path equals simulate path grid guard.clone. Okay, so now that we know the guard's original path, we can check each location she would step through, or we can traverse all of the locations she would step through and consider that location as a potential new obstacle. Place an obstacle there and rerun the simulation. This is going to require that the simulation detect a loop. Oh yeah, that's new. Because otherwise, if we end up in a loop, that simulate function is never going to return, and I will use up all of my memory populating the result. So simulate path is now going to return two values, loop detected and path. And for distinct locations, I'm just going to ignore it. For looping obstructions, I'm going to ignore the loop detected. Okay. Now, so far, there aren't any loops. So it's safe for me to do this. But now I have to start telling it that there is a loop. And I'm going to want to write some code to test this. Test that simulate path detects a loop and bails out. So we already know how to create one loop. So simulate path detects loops. If we just do this, it's not find guard that I care about. Let the guard equals find guard on the grid, and then let loop, and I don't care about the path this time. Simulate path on the grid and the guard. Oh. We'll call it looping. Assert that we are not looping. This is bad. We'll call it loop detected. Okay. Right. Okay. So this should pass still. Cool. Now we're going to modify the grid and do it again. So I'm going to make the grid mutable. I want to assert that a loop is detected. So now this test won't pass until I've set things up right. So first of all, grid. So 0, 6 is going to give us oh, I need to make a mutability function for the grid. So we're going to jump into here. Following a pattern that I see in a lot of other Rust code. Elemute. See if I can get this right. A reference to a mutable character. Expected mute car, founded car, so is this? No. That just worked? That just worked. Um, 0, 6. And now star equals, turn that into an obstacle. And still not going to pass. Okay, so now we're going to run it. Use of moved value, of course. And, okay, simulate path detects loops. In what way is the test failing? Assertion failed, loop detected. But I've modified the grid such that it should never have been able to finish. I should have gotten an infinite loop. Wait, why is 0, 6? This has got to be wrong. I don't have any understanding of why I wrote that. 0, 1, 2, 3, 1, or 0, 1, 2, 3, 4, 5, 6. That should have been 3. And so now when I run it, this test should never finish. Yeah, it's not going to. Cool. Break it before it uses up my memory and crashes my stream. Okay, so I can modify the grid now. That's pretty easy. So, oh, this is going to be interesting. I don't know how long these paths can get. And the search is going to be progressively slower the longer the path gets. But basically, on every step, if path.contains guard, I want to return, because this is a loop that's being detected. So I've gotten a location, I've updated the guard appropriately. The guard is now at a location and facing in a direction that has already appeared on the path. I want to return. I'm really afraid that this is going to... I actually think this might get really slow, because we're starting to deal very much with higher, at least n-squared time complexities here. But maybe we'll get lucky. Maybe it'll be fine. In any case, that all by itself should be enough. Okay, so even on the test data set, I could see a little bit of time delay. Oh, wait, there's an easy way around that. Let mute past states equals a hash map past states dot insert, or maybe it's add guard dot clone if path contain not path past states. There's no reason we have to do everything on a single data structure. Is it insert? It is insert. Okay, that went a lot faster. Let's get a comparison here. Let's see. Where's my simulate function? Simulate took, oh, not as long as I thought. 15 milliseconds versus now it takes 36 milliseconds, so it might, despite my fears, it might have actually been well below the noise floor. Either way, it does work. So, here we go. Now we come back to the looping obstructions problem. So let obstructions equals hash set new. This is what we're going to return. So for location in yes, path dot iter. So each one of these is a full guard state. I don't care about that. So map g.location. So far, so good. This grid now needs to be mutable. I want to put an obstruction there. So grid dot elemute at location dot 0 dot 1. It's going to equal an obstruction. First, I'm going to assert that it's not, or that it is an empty space. Don't care. So we're going to turn it into an obstruction. Then we're going to let looping, I don't care about the path anymore. Okay. Now we're going to convert this back to a dot and then say if looping obstructions dot insert this location. Can that possibly be right? Let's see here. Simulate path. Yeah, that makes sense. And I don't want to insert, or yeah, I do want to insert it. No, it's not right. In what way is it wrong? It does not contain 8, 9. But it got all of the others. So let's check that this is actually right. So 0, 1, 2, 3, 4, 5, 6, 7, 9. Okay. Okay, that seems good. Let's see what we get from solving the real problem. We want the total number of these, right? How many different positions could I choose for this obstruction? So let grid equal grid from input format. I need to, yeah, okay. Looping obstructions for grid dot find the length of that, return the whole string, and run 6b. And we'll see how long this runs. Okay. Yeah, I kind of feared that this could be an issue. So what I'm going to do is go back and add a debug print. The advent of code people say that this should all be solvable in under 15 seconds on very old hardware. So clearly my algorithm is bad. Wait a second. I never use the guard's orientation. I can reduce the problem size. So I get the path, and then for the path I want to So let path equals path dot into iter dot collect as a hash set. And in fact, I don't care about the guard's orientation either. Why did I think the orientation was important? Maybe there's a more clever algorithm that I thought I would stumble upon where that would be important, but it's not going to be important here. Consider removing this call as the receiver is O. Oh, I'm getting it wrong now. Okay. So I am still getting back a list of guards, so I need to do more than just this. We're going to map g.location, then collect that into a hash set. Cool. Expected a hash set of usize. Usize got a reference to usizes. That's a little weird. There we go. Try this again. There's already a lot more noise in the system. But it only has to check 4,000 locations now. What was that? 4,602. Start over. I probably should have made that more digits of precision. But yeah, here, it's just going to run. We've now checked 1,000 locations. There's almost definitely a lot smarter way to do this than I've come up with here. I just hope this is the right answer. It'd be really embarrassing if I've let my machine crunch along like this and I've got the wrong answer. Okay, looks like there are 1,704 locations where I can put an obstruction. So, let's try it. It's too high. Okay, return to day 6. What am I missing? What did I do wrong? Oh, wait. I included the guard's initial location, and it specifically said... Okay, 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 okay. I've got a list, right? A vec right here? Yeah. Bracket 1 dot dot. That's probably... No. It's not right. That's probably right. I'm gonna run it again. 1704. That's what I put in. If I get a higher number, then I'm really far off. But yeah, gotta remove the guard's initial position. In fact, the problem set even warns me. The new obstruction can't be placed at the guard's starting position. The guard is there right now and would notice. And then yeah. Because the first thing that I put into the path is the guard's starting location. That's necessary to figure out the number of distinct locations that the guard is going to visit. I am out of water. Anyway, this is almost done. The original answer was 1704. I expect this to be 1703, and I expect that to be the right answer. Fingers crossed. I got 1704 again. What? What? Uh-oh. I don't know what I'm doing. It's still checked. 4,600. Oh. Wait. No. What? Oh, the guard crosses over her first location a few times. Can't put anything there. Okay. So let's take this out. This wasn't wrong. Like, you'll note in the first run with the first solution, I checked 4,601 locations and got 1704 results. I once again checked 4,601 locations and checked 1704 results, even though I removed a location. Well, the guard walks through that location again. So I actually need to figure out what the guard's starting location is. And then once I have the hash set, I need to remove it. Expected types, unexpected reference. What? I expected... Oh. Borrow that, and then I'm going to make an assertion here. Path.len is 4600. Okay. It's still the same. What? Why is it still the same? Remove a value. Removes a value from the set. Whatever. Returns whatever. What? So assert path.contains start.location. Then we remove it. Then we assert not path.contains start.location. I'm very confused. How can those two statements be true? First, the path contains start.location, then it doesn't contain start.location. Contains 4602. That's okay. This problem just got hard because I don't know why it's wrong. So I know now that I'm definitely removing the starting location. Enumerate. Enumerate is 0 based. Length is not. I was looking at that list and I was seeing that I hit 4,601 elements. But enumerate is 0 based, and I was looking at the printout of the indexes. It was actually hitting 4,602 elements. Okay. I still think the answer is going to be 1,703 places where I can put an obstruction to make the loop. Copy that and paste it in. And that is the solution. Oh boy. I never even wrote a test for this. Oh, yes, I did. So I'm going to paste that there, assert EQ. We'll say looping obstructions.len of grid is 1703. Let grid equals grid from. I'm probably not going to be able to leave this test in place because I don't want my test suite to take 2 minutes every time it runs. We'll see. This is probably still going to be slow. I don't know. I'll let that run to completion. I don't know how to do it any faster though. Yeah, it's yeah, I'll probably have to go look up some other solutions to see how other people made it run more quickly. There might be some kind of memoization of paths, though I don't really know how that would be. I guess there could be some clever tree things where you calculate out one path, and if you ever end up on 45 seconds, if you ever end up on that path in the same direction, then you already know what the rest is, and you don't have to calculate it. But then you also have to be able to invalidate big chunks of that data set to take into account that obstacles have been placed later in the path. So yeah, I don't know how to do this more quickly than in 45 seconds. Now, admittedly, this is 45 seconds on 5-year-old hardware, but they do say everything is solvable within 15 seconds on 10-year-old hardware. I don't know. Possibly somebody more clever than me. Let me know. Maybe I'll find out when I look up somebody else's answer. But I think we're going to call it quits. In fact, I don't think. I know we're going to call it quits there. If you're still here watching, thank you for continuing to watch. I hope you learned something from it. I hope you enjoyed it. Share it. Subscribe to the channel. Watch me live on Twitch. I'm doing this almost every night, starting at 9 p.m. Eastern time through whenever, like I said at the beginning, whenever I burn out on Advent of Code. Leave a comment if you have any suggestions on how to make this better. With that, I bid you all good night. See you tomorrow night.